This lesson is going to be in two parts. We will do part A for hypothesis testing for proportions. And we'll start off with 8.3, testing a claim about a proportion. When conducting an hypothesis test for population proportions, first check to ensure that the following three requirements are met. Number one, the sample observations are a simple random sample. Number two, must meet the conditions of a binomial distribution, which means you have to have a fixed number of trials, fixed probability with only two outcomes, and the one not mentioned that we need to consider is independence. Number three, the conditions n times p must be greater than or equal to 5, and n times q must be at least 5. Both of those conditions must be met. Let's look at example 1, reality check. Based on recent information from the National Cybersecurity Alliance, 93% of computer owners have antivirus programs installed on their computers. In a random sample of 400 scanned computers, it is found that 380 of them, which is 95%, actually had antivirus programs. Use the sample data from the scanned computers to test the number of computers with antivirus programs and determine whether it is different than the 93%. First, let's verify that the three conditions are met for hypothesis tests involving proportions. Number one, the 400 computers are randomly selected. Number two, it is binomial because there are only two possible outcomes. The computer will either have virus protection or not. We will assume independence. And number three, n times p and n times q both exceed 5. So let's look at the p-value method. First, we state the null and alternative hypotheses, H0 and H1. The null hypothesis always states the original claim. The alternative takes the opposite claim. Notice that the null takes the equal sign, and for our class, that will always be the case. We're testing the claim that the percentage of computers that have antivirus is not 93. So the alternative hypothesis would take the claim that P is not 93%. And since this is not equal to, this is going to be a two-tailed test. In English, the null hypothesis states that the proportion of people who think they have antivirus protection is equal to 93%. The alternative hypothesis states the opposite. The proportion of people who think they have antivirus protection is not equal to 93%. Now we are doing a 95% confidence level. So we know that the mid region here is 0.95, which means that the tails have a total of 5%. That would be the alpha level. And if we split that 5%, each tail has 0.025, which is 2.5%. Now let's do the calculation using the TI-84. To perform this calculation, we're going to do the one-prop z-test. And when we call up the one-prop z-test, we will enter the null hypothesis's argument that the null value is 0.93. The x value is 380. And n is equal to 400. And again, we will choose the not equal to, since this is going to be a two-tailed test, and then we calculate. Now the 380 and the 400 came from the problem itself, because we sampled 400 people, no, actually 400 scanned computers, and we found that 380 of them actually had antivirus programs. So X is going to be 380 and N would be 400. Notice that not only do we get a z-score, which we could use, but let's look at the p-value. The p-value is 0.1169, and 0.1169 is greater than 0.05. In other words, the p-value exceeds the alpha level, and whenever the p-value is greater than the alpha level, we fail to reject the null hypothesis. So what did the null hypothesis claim? Well, if we go back up, the null hypothesis claimed that the percentage of computers is 0.93. And if we fail to reject the null, then we would simply say that we do not have sufficient evidence to reject the claim that 93% of computers have antivirus programs. In other words, it appears that the null hypothesis wins this argument, so to speak. Example 2. Now let's use the same data from example 1, but this time we're going to claim that the percentage of people with antivirus software is greater than 93%. Well, greater means it's a right-tailed test. So all of the alpha value, the 5%, would be in the right tail. So we would go back to the one prop z test. We would enter the null's claim for the proportion, 0.93. We would still use the 380 for X, the 400 for N. The only difference is we would select the right arrow because it's a right-tailed test. And the p-value is 0.0585. But again, 0.0585 is larger than 0.05. And when the p-value is greater than the alpha level, we fail to reject the null hypothesis. Example 3, finding the number of successes. A Harris Interactive survey conducted for Gillette showed that among 514 human resource professionals polled, 90% said that appearance of a job applicant is most important for a good impression. What is the actual number of respondents who said that appearance is most important for a good first impression? Well, if 90% said that appearance is important, and we have 514 people surveyed, then 90% of 514 would give us 463 people after we round up. Example 4, do people lie about voting? So we did a survey of 1,002 people, and 701 said that they had voted in the recent presidential election. Voting records, however, show that 61% of eligible voters actually voted. Tests claim that the true percentage of voters is not 61. Well, remember that the null hypothesis will always take the equal sign. So the null is going to argue that the percentage of people who actually vote is equal to 61%. And since this is not a right or a left tail claim, because we don't see greater than or less than, we're going to go with not equal to 61%. That would be the alternative hypothesis. Now, why would someone make the claim that the percentage of voters is actually different? Because they did a survey and they found that 701 people out of 1,002 claimed to have voted, which is almost 70% of the population. So perhaps after doing this survey, they came to believe that maybe the 61% is not accurate. So they're testing that claim that the number is actually different than 61. Not greater than 61. That's not what's in the narrative, but not equal to 61. And this is what the sketch would look like. Since again, this is a two-tailed test, we're going to do the alpha level of 0.05. If we split that into the two tails, that's going to be 2.5% in each tail. We will do the one prop Z test. We will put in the Knowles claim for the proportion, 0.61. We know that 701 out of 1,002 participated in the survey and claimed to have voted. If you look, the p-value is 0. Now be very careful when you read this output. At first it appears to be very large, but if you look to the far right, you will see an E. That E means that this is practically 0. In this case, the p-value is less than the alpha level, and when the p-value is less than the alpha level, we reject the null. If we reject the null, then we do not have enough evidence to conclude that the percentage of voters is equal to 61%. Example 5. Let's use the data from example 4, but test the claim that more than 61% of eligible voters actually voted. This would actually be the same setup as before, except this time, since it's a right-tailed test, we would have to employ the greater than symbol. And again, we get a p-value that is 0, or very close to 0. And since the p-value is less than the alpha level, we will reject the null. And we have enough evidence to conclude that the true proportion of voters is greater than 0.61. Example 6. In a survey of 880 U.S. households, 149 households used email. Use this data to test the claim that less than 20% of U.S. households use email. Use a 5% significance level. This time we're going to use the confidence interval method. To use the confidence interval method, we use one prop Z interval. One prop Z interval. When we go in to use one prop Z interval and enter the information needed to run the program, we get this. This tells me that the true percentage of households that use email is somewhere between 14.45% and 19.41%. Notice that 20% is not included in the interval. So the answer is no. Therefore, we reject the null hypothesis. We have enough evidence to reject the null. Therefore, the conclusion would be we are 95% confident that the true proportion of U.S. households that use email is between 14.45% and 19.41%. So 20% appears to be too big. Example 7, computer usage in schools. In a survey of 500 students aged 12 through 18, it is found that 82% use computers in school. Test the claim that the proportion of students aged 12 through 18 who use computers in school is equal to 3/4. Well, remember that the null always takes the equal sign. And again, since they did not specify more or less, we will just have to do an alternative claim that is not equal to. We will run the one prop Z interval. We will put in 410 for X because 82% of the 500 students use computers in school. So X would be 410, which is 82% of 500. The N value would be 500. We're doing a 95% confidence level. Once we calculate, we get a confidence interval of 0.78633 on the low end and 0.85367 on the high end. Now look at the null hypothesis. The null hypothesis claims that it's equal to 0.75. But 0.75 is not on the interval. It appears to be lower than the interval, and therefore we have to reject the null. We are 95% confident that the true percentage of students who use computers in school is not equal to 3/4.